Hello and welcome to the fifth and final video on the D1 chapter, Algorithms on Graphs. Here is the starter question for the nearest neighbor algorithm. Determine if the path starting at A or the path starting at F is shorter using this algorithm. So starting at A, I would have B. Let me get rid of that. And that. And A was 1, B is 2. 25. Now I'm at B, I'm going to be going to D. You can see this is almost the same as the previous video, but I've added in the G vertex that was missed off previously. So that's a 24. Now with the nearest neighbor algorithm, I have to look at column D, and the best one there is the 35 to F. So now F is in the path. Column F, we're looking at 27 to C. So far, same as before. In the C column, it's now 29 to G, which we didn't have before. And in G, I'm forced to use this to get to E for 31. Total weight there is 171. Now I'm going to clear the screen to do the whole thing again in blue, starting at F. So I delete F, and the best option for F is to go to C, as before. When I'm at C, the best option is to go to G for 29. That was 27. When I'm at G, the best option here with all these options is to go to E for 31. That brings E's column into play. 27 is the best option there to get to B. Now I have to use B's column. 24 gets me to D. And then I have to finish getting to A from D for 28. And that gives me a total of 166. 166 is less than 171, therefore F starts the shorter path. In this video, we're looking at Dijkstra's algorithm. Now, Dijkstra's algorithm is used to find the shortest path between two given vertices in a network, but you don't need to use all the vertices. You're just trying to get from start to finish in the shortest possible path. So not all the vertices need to be included, which almost certainly means that not all of them will be, although most of them will be labeled as part of the algorithm. However, not all of them need to be labeled. We'll talk about exactly what I mean by labeled in just a moment. Because this algorithm uses labels and it might look a bit weird, but in an exam, getting these labels correct is where all of your marks are going to come from. So whether you can see the shortest path by inspection or not doesn't matter. You must get the numbers in these labels correct. And the labels will look like this. You'll have a box, and the box will be split into a top and a bottom half. The top half split into 3 pieces. One part will already be labeled for you in the exam answer booklet, and that will just be the label of the point, whatever letter is labeled on the graph for that point. Then you've got this box here. This is where you're going to number the vertices according to when they were labeled. So this first one, if you have to start at A, for example, you'll put a 1 in this box because that will be the first one that is fixed. What I mean by fixed is it will be fixed on the shortest possible distance to get from A to this point. And this first one will be really easy because it will always be a 0. To go from A to A is a 0 distance. You don't have to go anywhere. That's why that will be fixed before you even start. So this will be the letter of the point. This will be the order in which you have fixed their shortest distances from your start point. And this will be what that shortest distance is from the start point. Now this box down here on your first point won't have anything in it because these will be the working values, the values that you have as you go along before you've finalized what that shortest distance is going to be. But these numbers in this working box are also important. Don't consider this to be like a scratch box where you can write anything you like. These must come up in the order the examiner is expecting, otherwise it implies that you've done the algorithm incorrectly. The diagram will all be given to you in the answer booklet. You'll just have to fill in the boxes in the correct order. Okay, let's have a look at the algorithm. The algorithm is this. You label the start vertex 1, like I just showed you, in the top middle box, and its distance 0 in the top right box. Then we start the algorithm proper. You're going to update the working values, i.e. the shortest distance from your starting point to that point, and you'll replace it if you found it's now smaller because of what you've just labeled. And you're doing this for the vertices directly connected to the vertex you've just finalized, i.e. labeled. Then you look at all the unlabeled vertices that do have working values, and you label the one with the smallest working value, i.e. you're fixing its distance. If there's a choice, choose either one. Then you repeat until you get to your final destination vertex, and it is labeled. So not just working values, it also needs to be labeled. This will make more sense as we go into an example. That will be the finished process. Then you find the shortest path, which is what the whole point of the algorithm is, by working backwards. That should be fairly easy, unless it's quite a long path, but it should be easy because you'll have worked your way through it in the minutes before doing this. However, you might have to justify your answer. If you have to justify it, if you have to explain how you know that it's the correct path, then you have to show the difference between the labels equals the arc length. Again, that'll make more sense as we do an example. So here's a graph. This is from the textbook. Use Dijkstra's algorithm to find the shortest route from S to T in this network. So it's giving you the start point, it's giving you the final destination. For this first example, I'm going to keep the algorithm on the screen as well as the answer booklet page. This is what you would get in the exam answer booklet. But let me be clear, you will not get the algorithm given to you. I'm just leaving it there for now while we work through this first example. So label the start vertex 1, we're starting at S. So straight away in your start vertex, wherever that is, you put a 1 there and a 0 here. Like I said, that indicates this is the first one that you have labeled with its final distance, and the final distance from S to S is 0. Now we update the working values of all the vertices directly connected to S. So S goes to A, B, and C. So from S to A is 5, from S to B is 6, from S to C is 2. Okay, I've finished step 2. These are the only ones connected to S. Step 3, of all the unlabeled vertices with working values, that's these 3 that we just looked at, label the one with the smallest working value. So we've got 5, 6, and 2. 2 is the smallest working value, so I'm going to label this point. What that means is I'm marking it as a final distance. This is the second point. So if this is a 1, this is a 2. This is just keeping track of the order in which you're labeling them. But here, this is also going to be a 2, because it's the shortest number in this working value box. What that's saying is, from your start point, it takes a minimum of 2 to get here. And that's obviously just like that. But now I have to repeat, because I've just finished labeling this point. So now I have to update the working values of all the vertices directly connected to the one I've just labeled. That's this and this. B and T are directly connected to this. I don't have to consider S because S is already labeled. So from here to here, it takes 2 to get here. I'm using this distance and then adding this arc. So here I can get to B for a distance of 4. That is better than 6, so I must put that in the box there. That's saying instead of S to B for 6, I can get there quicker. S to C to B for 4. But I also need to mark up here. So there's a 12 here, but I've already got 2 to get to C. So 2 plus 12 gives me a 14 working value to get to T. Now T is my final destination, but that's a working value, that's not a label. I have not yet finished. I have, however, finished this step. I've updated all the working values from C. Now, of all the unlabeled vertices, including A, which I didn't do this turn, but which is unlabeled, I need to choose the smallest working value. So I've got 5, 4, and 14. 4 is my smallest working value, so I'm going to label B. In here, this is the third one that I've labeled, so 1, 2, 3, and the shortest distance to get to here was this 4. So I've labeled this now. I need to update all the working values from B. Again, I don't update ones that have got a finished value, so I don't need to do these two. But I can now get to D. So it takes me 4 to get to B, and I'm adding another 4 here, so the smallest value to get to D currently is 8, and that's this route here. But B also directly connects to T. So I use 4 to get here, and then another 8 to get to T. That gives me 12. 12 is a smaller working value than 14. I must record that. That's telling me that it's shorter to go this route than it is to go this route. Now I finished updating all the values from B. Now I need to label the next smallest. 5, 8, and 12. 5 is obviously the next smallest. This is the fourth point to get its label, and 5 is the shortest distance from our start point. Now from A, I need to update all the working values. No working values here because it's already labeled. But this does have a connection. To go from here is 5, to add on another 4 would be 9. That is not smaller than 8. This is not a better route than this. Now I don't think you would be penalized for putting 9 after the 8, but you only need to replace it if it's smaller, and in this case it's not. So I'm going to leave the 8 there. I'm not going to put the 9 because it's not smaller than 8. That's all of the ones connected to A. Now I choose the smallest unlabeled one, and that is D, 8 versus 12. So D is the next one to receive its label, and the minimum distance to get to D is 8. Now from D, the only one to update is here. 8 plus 3 is 11, so I do have a smaller working value to get to T. Now T is the only one left unlabeled, so I put a 6 in here. This is the sixth and final one to get its label, and its label is 11. And that is part of what will often be your final answer. The question will often ask, what is the weight of your shortest path? And the weight here is whatever's in this box. But the shortest route is asking, what was the route? What were the vertices that you went through to get there? Now, because of the process, we know that's S, C, B, D, T. But if you need to prove that, if you need to explain where that has come from, and only do that if the question explicitly asks you to, then you need to take this number, subtract them, and show it equals the arc weight. That's the only way you can show that D to T was the last part of the route. If you do 11 and 4, you subtract them, it's 7. That's not 8. This was not the path that we used. 11 minus 2 is 9. That does not equal 12. So this is kind of an annoying part on the end if you have to justify it. If you don't, it's not too bad. We can see that we went from D to T at the end of the path. Then here, we went from B to D. We can show that by doing 8 minus 4 equals 4. And again, quickly show you 8 minus 5 is 3, not 4, and then there's no other options. So before D must have been B. From B, 4 minus 0 is not 6. 4 minus 2 is 2. So the path went this way. So before B was a C, and then 2 minus 0 is 2. So before C was S, and that's our beginning. So all of the calculations that I said there, all of the subtractions, are what you should write down if you need to justify that this is the route. If you don't need to, just write down the route. If you forget what it was, do what I just did there to refresh what it was. That's a full example. On to a second full example that is also an exam question. You can see that this is a big mark question. We've got 6 marks for doing this. You can also see it's going to take us some time. There are 10 cities here, 10 vertices, A through K without I. I suspect I is missed out of these things because it kind of looks like a 1 and nobody wants to get confused between letters and numbers. A bit of context here that you don't really need, but it does tell you that you're traveling from A to H. So we're starting at A and we're finishing at H. Continuing the context, she wants to minimize the distance she travels. Use Dijkstra's algorithm to find the shortest path from A to H. State your path, that's the letters, and its length, that's the weight. And again, what you'll have in the exam booklet is all of this drawn out for you like this. I've taken this right out of the exam answer booklet. So you've got all of this drawn to you, including the key, and 2 lines here for your final answers. But 4 out of the 6 marks are for what you will get in these boxes. You only get 2 out of the 6 marks for these final answers. So working through it, we start at A, so straight away this is a 1, 0. Then I update my working values, 13 and 22, from A to B and A to C. Between these two, B is the smallest, so that's the second one, and the label is 13. Then from B, everything that connects, it connects to C. 13 plus 7 is 20. That is smaller, so I need to update that. B to D, 13 plus 22 is 35. And B to F, 13 plus 32, that's 45. That's all of the updating needed, because these are the only 3 that directly connect to B that aren't already fixed. Out of these, C is the smallest. So C is the third one to get its label, and the smallest value there is 20. The only one connecting to C that isn't already labeled is E. 20 plus 16 is 36. Now out of my working values, 35 is the smallest. This is the 4th one to get its label. 35. That connects to E for 10. That would be 45, so I don't need to write that because that's bigger than 36. But it also connects to F for 9, and that would take that to 44, which is smaller than 45. It also connects to G for 12. That's 47. That's all the ones that connect from here. Between these 3, 36 is the smallest. That's the next one to get its label. 5th point labeled, 36 is the smallest working value. It only connects to F out of the ones that don't have labels yet. 36 plus 5 is smaller than 44 for 41. And that is now the next one to get its label, because there's only 2, 47, 41. So this is the 6th one, and 41 gets me all the way to F. From F, I need to update all of the ones that connect. That's J, K, and H. J is 28, so 41 plus 28 is 69. K is 22, so that's 63. And H is our final destination, but that's a 70. That's quite big. I can already see that there's a better option, because the 63 plus 6 would give me a 69 there rather than the 70. But regardless of that, I need to go through the process. Out of all the unlabeled vertices left, 47 is the smallest. This is the 7th one, 47. The only one it connects is with this 15 arc, 62. So that's actually a little bit better. 62 is now the smallest, so that's the 8th one to get its value, and 62. That connects up to J, which is kind of out by itself a little bit here now, for 67. And adding 6, 62 gives me 68. J, although it's not really going to help us at all, is the next one, so that needs a 9 for 67. It doesn't connect to anything that doesn't already have a label. And now 68 over here is the last vertex. 68 is the length of the shortest path. I can write that straight away there. And the route, the shortest path itself, that means the letters, I don't need to justify, but I do need to remember. So 68 came from the 62, and that came from the 15 and 47 here. This one came from here, and kind of surprisingly, after the starting bit, this one came from here. So this was actually the shortest route. I can check that by adding as I go. A plus 13 gets me to B. 13 plus 22 is 35, which is D. 35 and 12 got me to 47, which was G. 47 and 15 got me to the 62, which was K, and the 62 is what gave me the 68H shortest path. So there's a full exam question for you, and I hope that it's enough for you to have a go at Dijkstra's algorithm in exercise 3E. You can also now do the chapter 3 review exercise and review exercise 1, which means we're approximately halfway through the module, and maybe I'll see you on the other side in chapter 4.